Good afternoon, everyone, and welcome to today's ECA Learning Zone webinar with Eaton, all about the energy transition and the role of energy storage. Our guests today are Richard Molloy, up on your screen now. Richard is the Business Development Manager, Distributed Energy Management at Eaton. And on the other side of your screen, we have Caroline Royal. Caroline is Business Development Manager also at Eaton. Richard will be your main presenter this afternoon, and Caroline will be helping to answer your questions in the Q&A session at the end of the webinar. Speaking of the Q&A, you should see a question mark button on your screen now. Do please make use of this at any time throughout today's presentation, and we'll do our best to answer as many of your questions as we can at the end of the webinar. Finally, from me, a reminder that today's session is being recorded, and a full replay will be available on the ECA YouTube channel. That's at youtube.com/ECA live. And lastly, if you're an ECA member, do remember to log into the technical area of the ECA website, where you can access our technical support, guidance notes, editable certificates, and much, much more. That's at eca.co.uk/technical, and you can log in there. So that's enough from me. I hope you enjoy today's presentation, and over to you, Richard.
Okay, thank you very much, Omar, and thank you very much, ladies and gentlemen, for joining the session this afternoon. Before I get into the main topic of the day, I just want to give you a brief introduction to Eaton, for those of you who may not know who we are and what we do. Ultimately, we're a power management company. We help our customers use power, that's power in all its forms, more sustainably, more reliably, more safely, and more economically. Doing that, we have a global turnover of just under $21 billion US. We operate in over 170 countries around the world, employing some 100,000 people. And the image you see on the screen here is just some of our headquarter locations. Global headquarters, Dublin in Ireland, and then the European headquarters with which we're affiliated here is in Morges in Switzerland. This slide is just showing some thumbnails of some of the market segments in which we operate. We're actually split into sort of two divisions. We have an industrial and an electrical division within our business. I'm not going to go through each one of these segments, but I'll just pick out a few and highlight a few which are particularly relevant to today's discussion. So the first one to mention is data centers. Eaton are one of the world's largest suppliers of uninterruptible power supply systems, or UPS systems. And we provide a lot of the backup power and power security for some of the world's largest data operators, people like Google, Facebook, Microsoft, and so on. And the reason I pick out that one is because, of course, a UPS system is a power conversion system which takes an AC power source, converts it to DC, charges and manages a battery, and then reconverts it back to AC to support a load. And that core technology is exactly the same as the core technology we have in a battery energy storage system. So we have a deep expertise in that power conversion and battery management space. Next one I'll touch on is renewables. Of course, renewable energy is absolutely key to energy transition. And whilst as Eaton, we don't manufacture complete wind turbines or complete solar inverters, for example, we do supply many of the world's turbine and inverter OEMs with components that they use within their assemblies. So for example, a solar inverter may have contactors, fuses, circuit breakers, etc. within it. In a wind turbine, there might be medium voltage switchgear transformers and so forth. So quite a big market for us. And the third one in the electrical space to highlight is the utility sector. Clearly, we need to move energy from where it's generated to where it's needed. And as we see an increase in demand for electricity, the utility space becomes absolutely critical to managing that energy transition. So we do a lot of work in that space as well globally. The last item I'm just going to touch on is actually from our industrial sector, and that's vehicles. And the reason I highlight that is because we see some convergence now between our industrial and electrical sectors as we transition towards electrified mobility. And we manufacture and supply many of the tier 1 automotive OEMs with underbody components, so things like onboard converters for electric vehicles, fuses, battery connectors, battery breathers, control assemblies, and so on. So that's a rapidly growing sector for our business, honestly. And so we see on the one side, on the electrical, we're doing the if you like, the building side charging infrastructure. In our industrial sector, we're doing the vehicle side charging infrastructure. So there is a convergence there. That's all I'm going to say about Eaton. Move on now to the core topic of the day, which is energy transition, and specifically the role of energy storage within that space. Some of the topics we'll cover. First of all, we'll have a look at some of the key sort of milestones in the fight against climate change, just very briefly, high level, just as a sort of a reminder and a recap on that. We'll then look at some of the key drivers that we see happening during the energy transition, look at those in a bit more detail. We'll look at some of the changes that those are causing on our electrical system, and in particular some of the issues associated with reduced system inertia and the impact that has on our ability to provide frequency response services. So that's some of the problems that we'll encounter, but then we'll look at some of the solutions, and we'll spend a bit of time looking at various sources of flexibility before zoning in specifically to talk in more detail about energy storage and in particular battery energy storage. And then finally, we'll finish off with some discussion about how battery energy storage can help us integrate electric vehicle charging infrastructure within the built environment. Okay, so this slide's considering some of the trends in the energy sector, and clearly we've seen rising prices for electricity over a period of time. Just one sort of little caveat, this is a CPD certified seminar, so I haven't changed any of the slides. So I'll make a couple of comments where one or two things might be out of date, and this is one of them, which discusses rising prices from 2010 to 2019. We did see prices reduce a little bit during lockdown, but clearly with the recent sort of global geopolitical situation, we've seen electricity prices absolutely skyrocketing. Whilst they have stabilised a little bit over the last couple of months, pricing is still significantly higher than it has been historically. So there's a huge pressure on businesses and on individual consumers due to that cost of electricity from the rising prices. Conversely, when we look at battery pricing, the prices of lithium-ion batteries have declined significantly over that same period. Again, there's been a bit of a stabilising of prices through the recent global crisis, but in the long-term scheme of things, we still see battery prices continuing to reduce. So that's made lithium-ion batteries economically viable for applications within the built environment. And we're starting to see a growing interest there now that the business case is becoming stronger and stronger. And then the next point to mention is renewable energy generation, and we've seen renewable generation now sort of surpass fossil fuels in the UK electricity mix. And that happened for the first time in Q3 2019, and we've seen that accelerating, and that's a trend that's certainly set to continue. We've also seen the cost of renewables falling dramatically, and we now find that it's cheaper to build new renewable and new wind and solar resource to generate renewable energy than it is to build fossil fuel energy sources. And in fact, we forecast that it'll become cheaper to build new wind and solar capacity for existing demand than it will be to buy electricity from existing fossil fuel plants, simply due to the feedstock pricing that they have to contend with. So we speak about climate change, and obviously there's been a lot of discussion about climate change over many years, but really 1997 was the first significant agreement with the Kyoto Protocol, where there was an agreement to reduce emissions of carbon dioxide and other associated greenhouse gas emissions. And the Kyoto Protocol actually named quite a number of different greenhouse gases that were targeted for reduction in emissions. And they indexed those against carbon dioxide with what they called a global warming potential. So carbon dioxide was given a global warming potential of 1. So in other words, 1 kilogram of carbon dioxide released to the atmosphere has a certain impact on the environment. Methane, for example, has a much higher global warming impact than carbon dioxide. And depending on the source you look at, that's typically between 25 and 35 times. So it'd have a global warming potential maybe of 30. One of the greenhouse gases named in the Kyoto Protocol was something called sulfur hexafluoride, which some of you may have heard of. And the reason I mentioned that one is because that is the most aggressive greenhouse gas known to man, and that has a GWP of 23,500. So in other words, 1 kilogram of sulfur hexafluoride released to the atmosphere has the same impact on global warming as 1 kilogram of CO2. So sorry, let me rephrase that. 1 kilogram of sulfur hexafluoride has the same impact as 23,500 kilograms of carbon dioxide. So a very, very aggressive gas. And the reason that's important in our industry is because that's often used as an insulating medium in medium and high voltage switchgear. And there are now SF6-free equivalents available. At Eaton, we've been making SF-free switchgear for over 60 years. Most of the other major manufacturers also now offer SF6-free alternatives, although those have only fairly recently been coming to market. But if you are doing HV systems, MV systems, then really look to an SF6-free piece of switchgear. So slightly off topic there, but interesting and worth commenting because it's relevant to our industry. The next sort of key milestone was the COP21 Paris Agreement reached in 2015, where the world's nations agreed to keep the increasing global temperatures to well below pre-industrial levels and to pursue efforts to limit the increase to 1.5 degrees centigrade. Where are we nowadays? Well, when this deck was put together, the planet was warming by 0.2 degrees centigrade per decade, and temperatures reached about 1 degree centigrade above pre-industrial levels in 2017. Since then, we've seen significantly accelerating increases in temperature. And I'm sure you've all heard in the news that it's forecast that we'll see areas exceeding the 1.5 degree centigrade average during the course of this year. And just today, there's been a lot of reports in the news about Italy in particular experiencing a heat wave with temperatures forecast to be in excess of 48 degrees centigrade. And together with the sort of the torrential rain and storms that we've seen, that there's a clear visible impact on our weather systems from global warming. So that really emphasises the imperative to act fast and to act hard. And nations around the world are setting targets to try and reduce greenhouse gas emissions. And of course, the UK have a 2050 target to reach net zero, which we're all striving towards. So here we're looking at some of the key drivers we see in the energy transition, and there's probably 3 primary macro factors to discuss here. The first one is the electrification of our economies. So this is talking about the electrification of transport as we see a transition to electric vehicles. It's talking about the electrification of heat, and particularly switching from gas-fired space heating to things like heat pumps and direct electric heating, and electrification of industrial processes. An example might be switching from a gas-powered furnace to an electric arc furnace. We then see decentralization accelerating. So this is moving from the traditional centralized generation system to having millions of decentralized plants connected onto the distribution system and directly within our homes and businesses. And we also see digitalization as a key trend. Obviously, that's a key trend throughout modern life, but particularly we see that impacting the energy system as we have an imperative to monitor, to manage, and to control all those millions of connected assets to ensure we can maintain the stability of the system. So we'll talk about all those areas in more detail as we go through the discussion. So this slide is quantifying the scale of forthcoming change we expect to see in our energy systems as we transition to using more sustainable technologies. So here we expect to see an increase in global building energy share of 50% by 2050. Just from electrification of transport, we expect an increase in global electricity demand of 27% by 2030. So very, very rapid increase in energy demand through transport electrification. And through that digitalization piece, through the rise of cloud computing, we expect to see a 4-fold increase in the share of electricity demand from data centers in particular. Just to put that into context, today, data center energy consumption is equivalent to that of global aviation. And we expect to see a 4-fold increase in that as the data center market is really booming around the world. So it's absolutely imperative that that energy comes from non-carbon intensive sources. So clearly there's going to be a significant increase in renewable generation and probably a 50% increase by 2035. With that increased renewables base comes obviously greater variability in the system, so flexibility becomes critical. And with that, flexible energy assets such as energy storage will also see a big increase. And here we forecast a 13-fold increase on the installed base by 2030. Of course, all of those massive changes have some impact on the requirements of our system infrastructure, and we need to manage what we expect to be a decline in overall system resilience as a result of the disruption from this change. we need to manage and optimize 13 billion connected power devices with the digitalization piece accelerates. And with that comes some significant cybersecurity risks, which we need to manage. And here at Eaton, cybersecurity is an absolutely key issue for us. And we engineer above and beyond minimum cybersecurity requirements to help protect ourselves and to help protect our customers from bad actors in that space. And we've seen a big rise in that happening recently. So this slide is illustrating the decentralization of the energy system that I described. So on the left, we have the traditional architecture where we have a small number of large fossil fuel power plants generating electricity, which is transported across the transmission system through the local distribution system and on into our buildings and our factories and our homes, where we are effectively a passive consumer of that energy. As we move towards a more distributed architecture, we have millions of devices connected, and some of these quite large devices, we see energy storage facilities up to 100 megawatts being connected onto the transmission system. We see large assets being connected to the distribution system, and millions and millions of smaller assets connected in our homes and businesses in what we call behind the meter installation. So in other words, on the consumer side of the utility meter. And all of those assets are connected and controlled and managed by digital assets. And so we're showing here the connectivity and the data flows. So we start to see a very much more complex grid architecture evolving. And this is something that we describe as everything as a grid. And this is absolutely necessary to manage the stability of the system. And here we see the IT systems start to play an absolutely critical role in managing the stability of the wider electricity system. So we've discussed the growth in demand for electricity, and of course that energy can't come from carbon-intensive fossil fuel sources. It has to come from renewable resources, and the majority of that additional energy will come from predominantly wind and solar resources. And of course, wind and solar generators have very different characteristics to conventional generators, and that brings some new challenges for the grid operators when we introduce these into the electricity supply mix. And principally that's because they inherently have a variable power output, and that output depending of course on the underlying primary energy source. So in other words, is the sun shining and is the wind blowing? So that causes challenges for grid operators who have to manage imbalances in generation and demand and match those in real time. They have to manage disturbances as the variable supply, the supply varies, and maintain security of supply whilst managing grid congestion at times of peak network use. When we talk about grid congestion, historically that has been demand driven. So where we've had high centres of demand and not enough capacity in the transmission and distribution system to support that demand, so we've seen curtailments of load. What we now see more and more is that congestion being caused by excess generation, and either having more generation than we have demand on the system, or not having the capacity in the wires to transport that generation to where it's needed. So we start to see curtailment happening in the renewable sector, and clearly this is where flexibility again starts to play a key role. So when we think about a fossil fuel power plant, this is a large synchronous machine which is connected directly onto the grid. It consists of large rotating turbines, and those turbines have a huge spinning mass, and that mass carries a significant amount of inertia, which can help control brief disturbances on the grid system. When we think about the way a renewable generator connects to the grid, that's through power electronics. And a power electronic generator is an asynchronous machine which doesn't carry the same physical inertia as the traditional large generators. Now, you might expect large wind turbines, and particularly some of these vast offshore machines that we see being installed, to carry a significant amount of inertia. But when we think that the speed of the turbine blades spin at varies with the wind speed, that's not a constant 50 hertz inertia that we can feed directly onto the grid. So we have to go through a DC link and then through a power conversion to generate and synthesize a 50 hertz AC sine wave to synchronize with the grid and connect onto that. So again, it's an asynchronous machine. And similarly, solar is a native DC energy source, so that produces DC power, goes through the PV inverter to convert it to AC, and again synthesize that 50 hertz AC sine wave to synchronize with the grid. So I mentioned inertia several times, but what is it and why does it matter? So if we go back to our GCSE physics and look at Newton's first law, that states that inertia is the resistance of an object to a change in its motion. And in this example, the motion we're talking about is the rotating mass of a large synchronous generator. And that inertia is stored in that state of spinning at the same frequency as the grid. And when we talk about power system inertia, that's the sum of the multiple generators on the grid. They can act as a buffer to absorb sort of shocks to the system, if you like. So for example, if a large generator trips off or a large load is switched, we see a mismatch between supply and demand, and the frequency can fluctuate. So that inertia helps ride through and slow down those rates of change of frequency on the grid system. And so the grid's constantly adapting to the changes in supply and the changes in demand. And the grid operator has the task of matching those in real time. If we see variances, then we see frequency fluctuating. So for example, if we supply more energy onto the grid system than we have load being taken off it, then the grid frequency will start to rise, and vice versa if our load is greater than our generation capacity, so demand is greater than supply, then grid frequency can start to fall. Looking a bit more detail at frequency, and this is sort of talking about some of the challenges we faced, in particular during lockdown, when there was a huge slump in demand for electrical energy. We saw reductions of 17% during that first lockdown in spring 2020. And that caused some significant concern from National Grid, who sought and were awarded special powers from Ofgem in order to be able to disconnect generation without notice and without compensation to try and manage that. In the end, they didn't need to call upon that special power, and they were able to manage the reduction in demand by reducing the amount of generation being fed onto the system. But if we don't and the frequency starts to rise, then the grid protection relays will trip out on over frequency limits and disconnect the generation from the grid. When I talk about grid protection relays, these are the relays that are there to make sure that the generator complies with the engineering recommendations for connecting a generator in parallel with the public distribution system. So that's G98 and EREC G98 and EREC G99, which I'm sure many of you are familiar with. G98 covering small generators up to 16 amps per phase, so typically residential applications, and then anything over 16 amps per phase, G99. And within those standards, there are both high and low frequency set points determined, as well as voltage set points, to make sure that generators don't cause an undue negative impact on the system. They'll trip those generators off if things go out of tolerance. So at this period during lockdown, when we had this reduction in demand, it also coincided with excellent renewable generation conditions. So if you remember, it was beautiful weather at that time. We had great solar resources. It was lovely and sunny. It was also windy, and that led to a big increase in the percentage of renewable energy we saw fed onto the GB electricity system. And we actually reached almost 56% penetration of renewables. And the reason that's important to highlight is because it means that the system's actually rather better performing than had previously been predicted. And it proves that we have the capability to respond and to operate with a high renewables dominated generation mix. So we spoke about that slump in demand and the potential for over frequency causing generator trips. Similarly, if demand exceeds generation, as I mentioned previously, then we start to see the grid frequency drop. And again, those low frequency set point limits can be breached, and then that will cause the generator to trip out. And in this instance, this is a more serious condition because now we're starting to exacerbate the problem. Our issue is that we don't have enough supply to meet our demand, frequency goes down, grid protection relay trips out a generator, we've got less generation, frequency starts to fall, and this can lead to a sort of a cascading failure of the system. Ultimately, it could lead to complete GB system-wide blackout. So in a high renewable system where we don't have that system inertia associated with the central generation, those changes in frequency become more frequent, and they also start to occur much faster because we don't have that inertia to limit that rate of change of frequency. So it becomes apparent that the traditional means we've used for frequency regulation simply aren't fast enough to cope with the deviations of the sort of speeds that we're seeing. And we also don't have sufficient resource to compensate for large faults. So we really do need to increase the amount of fast-acting flexible energy resource that we have on the system. So I spoke quite a bit about the impact of frequency on the system, and this is an example of low frequency limits being breached. This is a particular event that occurred at 16:52 p.m. on Friday the 9th of August in 2019. And this was the first large-scale power cut that the UK experienced in over a decade. And swathes of the southeast of England were experienced a power outage at this point. In fact, more than 1.1 million consumers were disconnected from the grid. In less than 5 minutes, the system on the other transmission system anyway, it had tripped, recovered and been restored within safe frequency levels. And that was achieved through a combination of load shedding and through fast acting frequency response, of which 475 megawatts came from battery energy storage. So just to try and explain this graph in a little bit more detail, that the line that we see here is the trace of the grid frequency. National Grid have at their disposal, had in 2019 at their disposal up to 1 gigawatt of additional power to cope with these types of events, and that 1 gigawatt was designed to be representative of the single largest generator on the system tripping off. But during this event, as we can see, there were multiple large generator trips, and we lost 1.13 gigawatts of power within the first second after the first initial fault. And then we see the system start to recover down here as that fast acting response starts to take effect. But then we have an additional large trip here with Little Barford at 210 megawatts here and another 187 megawatts tripping here. So we see we haven't got enough frequency response, so we start to see that frequency plummet again. And this is when the grid frequency relays start to disconnect that embedded generation. We lose a further 200 megawatts and we reach a low point here at 48.8 hertz. And at that point, that's a threshold whereby National Grid, the electricity system operator, the transmission system operator, sorry, trigger what they call LFDD. That's low frequency disconnection of demand. And that is an indiscriminate isolation of supplies. And that happened, that they commanded the local distribution network operators to shut off consumer supplies in the southeast of England. And that's why 1.1 million consumers lost power. That sounds a draconian measure to take, but if they hadn't done that, then this curve would have continued to reduce and we'd have seen that complete GB system-wide blackout, and that would have had all of the issues associated with trying to start a black start from zero across the entire GB system. So this did have the desired effect, and this we can see the frequency starting to recover really quite quickly as the DNOs disconnect that demand, coming back within tolerance there. So end to end, if we look at the timestamps, first event 16:52:33, final event when before we get back into frequency tolerance 16:57:15, just under 5 minutes. As I said, that's the transmission system. It took a little longer for the distribution network operators to restore all supplies, and actually end to end this event lasted about 45 minutes. But the impact to consumers was felt for much longer periods than that in some instances. And principally, this was due to faults that were exposed on some trains. And if you recall, I said this was 5 to 5 on a Friday afternoon in the southeast. So there will be swathes of commuters trying to make their way home after their day in the city. After the power cut, it was found that many of the trains wouldn't reboot without manual intervention. And the train operators had to physically send technicians out onto the rail network to reboot trains and get them going again. So commuters were stuck in some cases for over 9 hours, which I'm sure wasn't the best start to their weekend. There was an awful lot of investigations and an awful lot of changes as a result of this particular event. So National Grid are now holding greater volumes of reserve to cope with this type of event. And if any of you are involved in the accelerated loss of mains change programme, where they basically decided that vector shift wasn't an appropriate means of frequency protection, and everybody had to change to rock off rate of change of frequency. This is the event that stimulated that accelerated loss of mains change protection to try and prevent these consequential trips of generators in this type of situation in the future. But it does really emphasize the criticality of fast-acting flexible energy resource to the overall operation of the power system. And it's apparent that certainly when this event took place, we didn't have sufficient resource to manage it. So there's a quote here, comes from Bloomberg New Energy Finance, which says that the energy transition will be faster and less costly if flexible energy technologies and energy markets become the cornerstone of the grid. And this is because we start to see an increase in the variability in our generation. So we have variable supply from solar and wind, but we also have an increasing variability in demand. And EVs and heat pumps, we have some level of control over when we can do that. We don't necessarily need to charge our electric vehicle at 6 o'clock when we get home from work. We have some control over that. And so having that flexibility to consume energy when it's available and reduce our consumption when it's not is absolutely critical to ensure that we can meet the UK's objective of a zero carbon electricity system by 2030, and to meet it at the lowest possible cost to consumers. So we've been into some details on some of the issues that we see through energy transition, and we've said that we need lots and lots of flexibility. So what are those sources of flexibility? So there's a number shown here. This is not an exhaustive list, but this is some of the key technologies that we see. And first one, and a very traditional one, is demand side response. So this is where a consumer has the ability to rapidly alter their electrical usage to match the needs of the grid during times of system stress. So that would be in response to a signal from the system operator. And traditionally, demand side response has meant typically reducing, but could be reducing or increasing demand from that signal. But as we see the rise of behind the meter generation, that can now, a building can now actually export grid during these events. So effectively, it looks to the grid like a net negative demand. And that can be very powerful at helping integrate these flexible energy resources. And it can also help avoid costs by reducing the amount of additional reserve generation we need to hold. So just to illustrate with an example of demand side response, that might be, for example, a supermarket chain might say that they can run their refrigeration, or they can run without their refrigeration without exceeding the temperatures in the freezer cabinets for, let's say, 30 minutes. So they may get paid to reduce their refrigeration load during particular periods. And they would do that, and they'd earn a revenue from having that flexibility. So that's an example of demand side response. We then look at interconnectors. This is quite an important one for the GB power system, and this enables the system operator to import or export power across a wide geography, and through different electricity markets in different countries. Today in the UK, we currently have a 6 gigawatt interconnector capacity in total. That comprises 3 gigawatts to France, a gigawatt to the Netherlands, a gigawatt to Belgium, and then 500 megawatts each to the north and south of Ireland. So a total of 6 gigawatts today, but another 7.5 gigawatts currently going through planning. And we've even heard talk of subsea connectors from Morocco to link Europe with African solar resource. So giving wide area flexibility to respond to changing weather conditions in different parts of the world. We then, of course, have energy storage, and energy storage can be in many, many forms. So we've got a number here mentioned. The first one, we say PHS, that's pumped hydro storage. So that's your traditional hydroelectric generator, where you've got a dam with a body of water pumped up behind the dam at a higher level than the outlet below. So we can release water through the dam, drive turbines in, and then that water goes out into the basin below, ready to be pumped back up when we need it again. So that's very traditional, but a very large capacity and high power asset, but limited scope because it relies on having the right geography to install it. We then have CAES and LAES, that's compressed air and liquid air energy storage respectively. Compressed air is a technology that may be very useful for longer duration storage, through pumping air into underground salt caverns, for example, and then holding that at pressure and releasing it again to drive a turbine. Liquid air energy storage, same but sort of slightly smaller scale. We're looking at here at cryogenic storage, so we hold that liquid, that air in liquid form at very high pressure. We have flywheels, we have supercapacitors, and of course we have batteries of a number of different technologies. These different technologies store energy in different forms. So we can have kinetic energy held in a flywheel. Another one is not on the list here, but we see gravity storage where we hold energy through gravity. We can store electrical energy directly, for example, in supercapacitors, and batteries were stored in an electrochemical format. And the key is that we can reconvert all of that into electrical energy, and also is critical is to consider the various timescales, because we need to consider energy storage from the millisecond timescale through to annual sort of storage regimes. One of the key advantages to battery energy storage is their speed of response. But I said we see very fast, rapid deviations to the grid frequency. So having the ability to respond in milliseconds is key, and some battery systems can provide a 0 to 100% response within the millisecond timescale. So that's really valuable to help stabilize a system where we have reducing inertia through the swap to decentralized systems. Other sources we should also think about: power to gas. An example there might be offshore wind driving a hydrogen electrolyzer to generate green hydrogen, which can then be burnt to generate electricity or used directly as a fuel for heat. We have power to heat. An example here might be where we see thermal storage becoming of greater consequence. That can be large thermal stores, and we see that, for example, molten sand sitting in concentrated solar power plants. We see it in smaller scale in residential, where we start to see things like electric boilers with phase change materials, people like Sunamp and Tepio doing that, and we see people moving back to thermal hot water storage, either direct heated, or we see that with heat pumps as well. Other sources: smart electric vehicle charging, and also a vehicle to grid, where we can access the stored energy in our vehicle batteries for flexible resources. So I've highlighted why flexibility, in particular battery energy storage, is critical to that energy transition. So we'll move on now to look in a little bit more detail at battery energy storage in particular. This slide is considering the different use cases for each of the main user groups for energy storage. I'm not going to go through each of these icons. I think they're fairly self-explanatory as to what they mean, but broadly we see the use cases split into 5 primary areas. Number one is saving money through saving money on electricity through time of use tariffs and through reducing demand. We see maximising self-consumption, optimising the use of on-site renewables. We can defer utility investments. We can maintain resilience by providing backup power, and we can generate additional revenues through providing grid ancillary services such as demand-side response and frequency response. So this slide here is showing sort of a stylized single line diagram of how an energy storage system might integrate to in a building. So we've got our grid represented over here at the far left, and we're showing our grid supply here as bi-directional. We can import energy from the grid into our building, or we can export energy to the grid. We're representing our metering here, and this line along the bottom, this is really representing our AC building power distribution system, with our traditional loads represented at the end here. So we've got our on-site generation here shown as photovoltaic, and that's most commonly what we see, going through its inverter to convert DC to AC and feeding into either feeding loads in the building or feeding out to export to the grid. Could be any renewable energy source. We also have our electric vehicle. This is shown unidirectional as a load charging from the building distribution system. With the advent of vehicle to grid, we might see that become bi-directional. Our storage system connecting in parallel with the main building distribution system. This is a bi-directional connection, so we can charge our storage from our solar PV and we can discharge it to feed our loads, or we can charge it from the grid and again discharge to feed our loads. We're also showing a backup facility here, so we have an output so we can feed backup power systems. In this slide it shows an electric vehicle being charged, but it could be any system that you want to support in the event of a grid outage. And this is key. This is the application control. This is where we have all of the different use cases embedded on the system. So it's the brains, if you like. And the yellow dotted lines are the data flows. So we're managing and controlling all of those different assets. So that gives you an idea of how it integrates into the system. Some of the key value propositions, and I'll go through each of these in a little bit more detail on the following slides. So firstly, we can improve our green credentials through that optimization of on-site renewables. We can provide resiliency through backup power and optimize how and when we use energy. We can use it to manage power flows and also to generate revenues, as I mentioned, and we can use it to support our electric vehicle infrastructure. Just to illustrate the image that we have on the slide here, this is our X-Storage compact system. This little screen on the front is the application controller I showed you on the last slide. That's an HMI PLC touchscreen interface. So we can stand in front of that and program the system, or we can access that remotely and replicate everything from anywhere in the world. What we've got on the screen is actually a 40 kilowatt, 50 kilowatt hour all-in-one system in a standard data center style battery rack, so 600 wide by 1000 deep. We can add a second rack with additional batteries, so it could be 40 kilowatts, 50, 100 or 150 kilowatt hours. And then we can parallel up to 5 of those systems together. So ultimately it goes up to 200 kilowatts with 250, 500 or 750 kilowatt hours of stored energy. So ideally suited to sort of small to medium commercial, light industrial type applications for behind the meter storage and flexibility. Just to talk through some of those applications in a bit more detail, this is the maximising self-consumption function. So we're illustrating here this on a domestic type example, probably the easiest to understand it this way. So we see here, during the day, we've got a 4 kilowatt solar on our roof, for example. It's busy generating energy, but the kids are at school, we're out at work, so we don't have any demand for that energy in the home. That gets exported to the grid, and typically we get paid a very low rate for that export energy. We come home from work, kids come home from school, we start cooking dinner, using energy, and now we're having to import that from the grid at a much higher cost than we achieved for our export. So if we have a battery and we have the ability to use that excess power during the day, store it in the battery and defer its use until we come home and we need that power, then we've got that zero carbon and effectively zero cost energy that we can use in preference to importing energy from the grid when we come home. So really, this is the single strongest driver that we see for the installation of battery energy storage in behind the meter applications. And this particularly with what's been happening with energy prices, this becomes economically extremely attractive. We then have the ability to provide backup power, so clearly there's savings associated with that if we can maintain systems during a power cut. In a residential example, probably we wouldn't back up everything. We'd perhaps not back up things like power showers, washing machines, cookers and so forth, but we'd want to keep the AV systems running, security, heating controls and so forth. We'd want to keep running, so we'd probably back those up. Similarly, in commercial applications, you'd pick the systems you need to support and load shed those that you didn't. Peak shaving, this is the second biggest use case we see for battery energy storage, and this is where we see either restricted availability of supply from the grid operator, from the distribution system operator, or we see increasing loads behind the meter in buildings, and often that's due to adding things like EV chargers and heat pumps where we have a significant additional load added. So using energy storage allows us to store energy in off-peak times when the building demand is lower, and then support those high points of building demand. So we can either reduce our supply capacity or avoid breaching the supply capacity we have. Just to illustrate this with an example of a large retailer we recently worked with who were building a new store in Hampshire, that they only had an available supply from the grid operator of 250 kVA. To get reinforcements to the supply to increase that, was needed reinforcements up to 132,000 volts, which apart from being astronomically expensive, was also not possible until at least 2030. So they got a 250 kVA available, and that was the limit. They had a model store demand of over 300 kVA during the entire daytime trading hours. It's actually a 24-hour store, this, but overnight demand was much lower. So we could charge a battery overnight and use that additional energy then to support that gap between the 250 kVA supply and a 300 kVA demand during those trading hours. And that alone was the business case for the battery energy storage. We're also doing some solar self-consumption there as well now, but that wasn't part of the original business case. Next one is load shifting. So this is simply changing the time in which we consume electricity, and this is typically through making use of tariff differentials at different times of day. So for example, you might have a cheaper overnight tariff rate versus your daytime, so you can charge your battery overnight and then use that stored energy to offset energy you might otherwise have to import during the day. Sometimes we see more complex tariffs, what we call pass-through tariff, where all of the different constituent elements of an energy bill are passed through to the consumer, and that then exposes that consumer to some of the other variable charges. And for example, that would be things like distribution use of system or DUOS charges, which have a green, amber and red zone, with the red zone having the highest charges, typically in that early evening period, and most usually 4 to 7 p.m, but it does vary a little bit geographically. And if you can reduce your consumption, then if you're exposed to that price differential, then you can have a bigger impact on your energy bill. We've spoken at some length about frequency regulation, and clearly the storage can help with that frequency regulation. Here we see that we can manage that imbalance between excess supply and demand, so we can discharge when frequency starts to drop to support the system, and we can charge when frequency starts to rise again to support the system. And as I mentioned, that switch from charge to discharge can happen in just a few milliseconds. To respond to those rapid changes as we see the fluctuation in supply and demand, the speed of that fluctuation increase. Okay, we'll just finish off looking at the integration of electric vehicles and the impact that they have on the grid. And this is from a study we did on sector coupling, which was undertaken by Bloomberg New Energy Finance. And this looked at the impact of widespread uncontrolled EV adoption on the transmission system and the distribution system. And this was based on a 50% adoption rate, so 50% of homes owned an EV. And as I say, this was looking at if charging was unmanaged. And this showed that if people come home from work and plug their vehicle in, as would be the natural inclination with normal consumer behaviour, then we'd see something like a 15% increase in demand during that early evening period on the transmission system. And whilst that's a reasonable chunk of growth, it's not expected to be a significant problem in most areas on the transmission system. We've seen over a number of years quite significant reductions in demand at the transmission level, as we've seen energy efficiency increase through things like deployment of LED lighting and through things like industrial loads moving offshore. So there's capacity on the transmission system by and large. But we'd also recognise that the adoption of electric vehicles and other electric technologies like heat pumps is unlikely to be uniform across the country, and we'll see sort of hot spots where adoption rates are faster and levels of penetration are deeper. And in these areas, Bloomberg's modelling showed we might see up to a 30 to 40% increase in power demand at local distribution level. And that's a significant problem because the local distribution transformers simply won't be able to keep with that. Simply won't be able to cope with that. So that does present some challenges. And I think really illustrates that managing EV charging and managing heat pump demand is really crucial to help prevent massive increases in cost through overbuilding distribution systems. And so we'll achieve that partly through the mandated smart charging, the electric vehicle smart charge point regulations, which came into force last year, which mandate that by default a private charge point has to be set to charge off-peak times, and through things like vehicle to grid adoption, which will allow us to use some of the energy in our battery to support the system at times of stress. And again, heat pumps with that thermal energy store have some discretion about when the pump has to run in order to provide the levels of comfort that the building demands, and that goes hand in hand with increased levels of insulation, which is really critical to the GB energy system. So this slide's illustrating what we describe as a non-wires alternatives to grid reinforcements, and it's really the peak shaving application. But where we see this coming to the fore is where we're integrating electric vehicle charging infrastructure in the building, because that can represent a significant additional load. So we may be able to install a certain amount of infrastructure on our existing supply, but there's going to get to a point where our supply capacity isn't able to cope with that additional charge power that we require. A, because of the number of charges we need, and B, the user experience we need to provide and the speed of charging we need to provide for the users. So that might lead to us seeking a grid supply capacity upgrade. And as I alluded to in the example about the retail outlet I mentioned, that upgrade may be colossally expensive, or it may not be available in a short timescale. So if we can use battery energy storage to supplement our grid and to provide that peak demand when it's needed, then we can provide that infrastructure and that user experience without necessarily having to increase the grid supply capacity, hence reducing the cost and reducing overbuild of the system. And of course, that storage may also be able to provide other services like providing backup power, and maybe even earn revenues for providing grid ancillary services through demand response programs and frequency regulation programs and so on. So just to summarise, really on-site renewable storage, EV charging and other flexible technologies, really kind of a marriage made in heaven, where we can integrate and manage all of those different assets to help us control our energy supplies, to help us manage our bills, and to help us improve our sustainability. We also improve resilience, not just of ourselves by providing backup power, but also of the wider system by helping contribute to grid stability. So we move from that traditional passive consumer of energy to being an active participant in the wider grid system. And of course, absolutely crucially, it enables us to make the maximum use of those on-site renewable energy resources. Oh, oops, apologies, skipped on too far there. Okay, so that brings me to the end of the presentation, so we can move to questions now. Omar, did you want to moderate a Q&A session?
Thank you very much, Richard. So before I hand over to Caroline to talk through a few questions that have come in, just a reminder from me that today's session was CPD accredited, and everyone with us on the live webinar today can access a certificate. So you'll receive an email shortly after this webinar concludes with a short form to fill in to access your CPD certificate. And now over to Caroline with a few audience questions.
Yeah, thank you, Omar. So Richard, we have one that came in during the presentation, which I've answered in a form, but maybe you can you know, have a look as well. So a customer came in from Stephen saying that he's experienced where designing a net zero building, the grid cannot take the full renewable load back into the grid produced from the PV. So how do you see the grid becoming bigger to allow renewable loads back onto the grid? And my answer was very much about, you know, the grid needs modernising. I saw something the other day that the average age of a transformer on our grid is about 64 years old, and they're not designed for now and the capacities and loads that we've got now. So is that your take, or have you got something else you can add to that?
I can expand on that, Caroline. And I think where we see PV designers traditionally have designed what they call right-size PV systems. So the PV system has been sized so that the building occupier will consume probably 85% plus of the PV generated power with limited levels of export. We're starting to see a move now towards maximising roof space and just putting as much PV capacity on as the building can take. And that's obviously leading to greater levels of export. But here we see really the combination of energy storage and things like heat pumps and EV charging able to utilise that on-site renewable energy to reduce the amount that's exported to the grid. We also have EREC G100 coming into play here, and I'm sure that the gentleman who's asked the question is probably familiar with G100. That has recently changed. In fact, on the 1st of May this year, we went to G100 issue 2. And that now sets limits sets regulations for customer import and export limiting schemes. So we can have an export limit scheme to prevent our system exporting energy above this prescribed limit from the DNO to the grid. And sometimes that limit may be 0. For our own storage compact, we have a G100 issue 2 type tested compliance certificate, so we can provide that. And with our energy management system, we can also manage other third-party assets, so things like throttling PV inverters and so on. But G100 does also set limits for how much PV capacity can be connected to the building, and that's based on a number of factors, including the thermal constraints on the network, the fuse rating. For example, it can't be more than 1.45 times the supply fuse rating, and it will also look at protection settings, and the DNO will determine what they describe as a state 2 limit, which will be the maximum amount of behind the meter generation that you can install. I have to say, one frustration we see in the renewable and the storage industry is that the grid operators treat battery energy storage and PV as additive. So they consider if you've got a 100 kilowatt PV system and a 100 kilowatt battery, you've got a 200 kilowatt behind the meter generator. Actually, the reverse is true, because the battery storage will reduce the amount of export, because it's going to consume energy that's being generated rather than it being exported, and it's going to release energy rather than it being imported. So it's a net benefit to the grid, but is treated as a problem, and that's something that we, along with some of the trade associations we belong to, have been sort of campaigning for fairly strongly for a long time. I hope that's gone some way to answering that question.
Yes, I think so. Just a couple more then. What's the most common reason people are looking to add battery storage to the buildings for?
Today, the most common reason is for maximising the use of that renewable energy. So exactly as I described, putting on as big a PV system as you can put on the roof, putting in battery energy storage alongside it, storing that excess renewable energy, and effectively reducing your import energy by the greatest possible percentage. And that's really driven, I mean, the cost of electricity, but bear in mind that commercial consumers haven't been privileged to have the same sort of price caps that residential consumers have. And we've seen commercial tariffs peak at up to about £1 a kilowatt hour, but regularly at 65 to 80 pence per kilowatt hour. We've seen big differentials in time of use coming in as well. But when you've got such colossally high energy rates, generating your own PV energy and storing it and any excess and using it on site, we've seen payback periods below 3 years for co-located systems like that. So really strong business case for doing that. So that's the number one. The second one I think I mentioned earlier is peak shaving, where we're seeing a bigger drive because of limited availability of grid supply capacity. And actually, this speaks to the question that Stephen asked earlier. The limited grid capacity and difficulty building out the grid. We see that also causing a challenge. So that peak shaving application comes in, and time of use where we see those bigger differentials in daytime and overnight tariffs again can start to make sense. And we see people looking at sort of hybrid use cases whereby you perhaps do maximising self-consumption during the summer months where you have a significant amount of excess, but maybe changing the way you use the battery during the winter months when there's less excess, to doing a time of use and application and charging your battery at cheaper overnight rates and then discharging during the day to supplement the energy you are generating from your PV system and minimise grid imports.
Fantastic. Thank you very much, Richard. I think there's just one more comment here from... Sorry?
No, go on. I thought we're close to time, but carry on.
I think we are close to time, but this isn't really a question. This is just a comment from Michael that I'll read out. He just says the grid will have to provide more incentives to invest in storage, as they're only offering a pittance for our electricity at the moment. Can you have a word, please? So if you know anyone to...
Unsurprisingly, I completely agree with that commentator. Yes, we are having words. Yeah, and there are no incentives for energy storage. And I think that there is a consultation being undertaken at the moment called REMA, which is the Review of Electricity Market Arrangements. And I think what we need to see coming out of REMA is appropriate reward for flexible energy technologies and appropriate reward for providing different services, not just capacity and not just energy, but providing system stability services. And the outcome of REMA may be that we see some stronger signals. And I think over recent years, Ofgem have actually diluted some of the price signals for energy storage by things like removing the triad, the transmission network user system, and moving to a flat rate charge, by things like flattening the delta between the green and the red zones in the distribution user system charges, and various other actions that have watered down the business case for behind the meter storage, and we need to see that coming back through appropriate electricity market arrangements. So hopefully there is some silver lining on the horizon, although we don't today know exactly what that looks like.
Okay, thank you very much.
Okay, Omar, I think we're about on time. Did you want to make any concluding comments?
Just a couple of closing points from me. First of all, thank you so much to you both, Richard and Caroline, for a fantastic presentation this afternoon. And thanks to our audience, to everyone who joined us today. Stay tuned for that email in a couple of hours with that link to get your CPD certificates. And again, this webinar will be available to watch back on our YouTube channel, youtube.com/ECA Live. That was it from me. So thanks once again to everyone, and have a great afternoon. Thanks. Bye, everyone.